Okay, so the cell notation, it describes what happens in the galvanic cell. So in the last video, I said a lot, right, about all the components and compartments in a galvanic cell. The cell notation is writing the general redox reaction that's happening, and it's sort of describing the flow of electrons in a galvanic cell. So the order in which we write from left to right. So on our left is always the anode, which has the oxidation half cell. So in that last example with copper and silver, we're going to write this oxidation step. Then we're going to write reduction on the right, which was our silver plus going to silver solid. We have a single vertical line that represents a phase boundary, right? So we write this in between our oxidation and reduction step, right? So from copper, we went from copper solid to copper aqueous, solid to liquid, or solid to aqueous solution. So we just write a single vertical line between those. Similarly with reduction, right? We went from aqueous silver to solid silver. So we would write a single vertical line between those. We write a double line to denote our salt bridge, and we don't include spectator ions. And what I mean by that is we only focus on the ions that are being oxidized or reduced. Okay, so let's look at an example. Let's go back to the same example that we had with copper and silver. So here's our cell notation. So we start with copper solid. We have a single vertical line going from copper solid to copper in aqueous solution. In aqueous solution, which is 1 molar copper nitrate. Then we denote the salt bridge with these two vertical lines. And the electrons, right, they flow. And so then we go from our aqueous solution of silver, which is in silver nitrate. Once silver plus ions are reduced, we result in silver solid. So we write this single vertical line between silver in aqueous solution and silver in solid, in the solid phase. So the other way we can write the cell notation is the exact same thing, but instead of writing the concentration of the aqueous solution, we just write the ions, right? So copper nitrate, in copper nitrate solution, we have copper 2 plus ions. So we go from copper solid to copper 2 plus, salt bridge, silver plus to silver solid. Either notation works. This notation feels like it's cleaner, but I just want to make sure that you're clear on the two different ways that we can write it. We can write it with the aqueous solution, or we can just write the charge on the ions that's being oxidized and reduced. Let's look at another example. Let's look at an entirely different example. So we have a different galvanic cell with magnesium at our anode, so magnesium is being oxidized, and we are reducing iron. So in this half cell, we have 0.1 molar magnesium chloride solution. We have our magnesium anode solid that when it is oxidized will be oxidized to this magnesium 2 plus ions. The electrons will flow through the external circuit through this platinum cathode. So the reason we have a different cathode is because sometimes what's being oxidized or reduced doesn't necessarily have a cathode or anode for it, right? So in the previous example, we saw that we had copper and silver. These are inert electrodes that allow electrons to flow through. We can also just use, we could have used platinum in that other example as well, right? So this platinum cathode is just our electrode that's allowing the electrons to flow through into our reduction half cell. And so we have this solution of iron chloride where we're reducing from iron 3 plus to iron 2 plus. We have our salt bridge, right, with our anions and our cations flowing in to balance the charge, and our external circuit where the electrons are flowing through. So I want you to pause this video and write all of the following. So you're going to write the oxidation half reaction, the reduction half reaction. The sum of these will give you the overall net cell reaction. So you can think of this as the oxidation half reaction, the reduction half reaction. Added together gives the overall redox reaction. And then I also want you to write the cell notation. So let's look at it together. So our oxidation half reaction, we have magnesium solid being oxidized to magnesium 2 plus. And it produces 2 electrons. Those 2 electrons are consumed, reducing iron 3 plus to iron 2 plus. When we combine both half reactions, this is our overall net cell reaction. This is our overall net cell reaction where we have magnesium solid plus iron 3 plus. Our electrons cancel out, yielding magnesium 2 plus plus iron 2 plus. So our cell notation, right, going from left to right, we're going to start with magnesium solid oxidized to magnesium 2 plus, right, in our 0.1 molar magnesium chloride solution. We have this vertical line for the phase separation between solid and aqueous, our double line for our salt bridge. Then we have iron 3 plus, right, which is in our iron chloride FeCl3 aqueous solution. And so if we have 2 solutions mixed together, we just separate them by a comma, right? So this is why I have both of these solutions here, right, for our reduction. And then our cathode is written last, our solid, which is platinum. So we always start with our anode and end with our cathode. And then we write what is happening as a result of the oxidation, what's being reduced, separated by the salt bridge. Whoops, I didn't mean to go. Okay, so again, we could write this instead of 0.1 molar magnesium chloride, we could have just put magnesium 2 plus aqueous. And here we could have put iron 3 plus, comma, iron 2 plus, this vertical line, platinum solid. Either one will work. All right, so summarizing what we've learned about galvanic cells, right? The types of reactions that we are looking at are redox reactions. So we have oxidation and reduction half reactions in each half cell. And by compartmentalizing or separating the oxidation and reduction, we have this spontaneous redox reaction that takes place where we can isolate the electrons, right, so that they can be the source of electrical energy. So in the half cell to the left, this where our anode is, oxidation occurs, and the other half cell where the cathode is our reduction. Each half cell consists of an electrode dipped into an aqueous solution, right? Which is our anode in our oxidation half cell and our cathode in our reduction half cell. And then we have a wire that connects the two half cells that allows electrons to move between the two, as well as our salt bridge that allows us to balance the charge buildup or the charge depletion in our two half cells. So this concludes our section on galvanic cells.